Okay, so I will already introduce our next speaker, which is Charley Lineweaver. He's an associate professor at Australian National University Planetary Science Institute. So his research interests are very broad, ranging from cosmology to astrobiology to exoplanets, evolutionary biology. So today he's going to talk about biology and the origin of information. And for this talk, we're going to do it a little bit differently because I've seen, you've probably also noticed that Charley really likes discussions. So I actually encourage all of you to ask your questions throughout the talk. I will monitor the audience and then Charley will repeat your question for the online audience. So it would be great if the sound team can leave my microphone on. So let's make it a nice and interactive talk. And Charley, the floor is yours.
Very much. Yes, I want to thank the Big Bang for making it possible, for the organizing committee to make it possible for me to be here. And I'm interested in this question about the relationship between biology and information. And yesterday, I understood from Seth Lloyd that just an electron hitting a photon, no, a photon hitting an electron was processing of information. And I wanted to say, no, you need biology to have any information at all. So I asked my friend Eric Smith, I said, Eric, what do you think of the idea of an electron being hit by a photon, and that's processing of information? And then I was thinking, well, wait a minute. When you have these virtual fluctuations in empty space, you know, we have lambda, we have these virtual fluctuations. Is that processing information, or maybe that is virtual processing of information? I don't know. When I asked Eric this, he said, Charley, what does processing mean? What do you mean by information? He's thought about this for a long time, and he's the next speaker, by the way. And he said that he can think of 20 different definitions of information before breakfast in the morning. So I was very confused. And after Tamara's talk last night, I heard that there was a Green Day concert over there. And I don't know if you could hear it. I walked over there and I saw hundreds and thousands and tens of thousands of people coming out of that venue. And I said, wow, what is wrong with Edwin's marketing skills? But really, then I said, wait a minute, all these people are getting some kind of information from this music. That doesn't seem like the kind of information we've been talking about. I think, well, maybe music has some information content that appeals to your emotional brain rather than the rational brain that we are dealing with here. So maybe there's some kind of difference between emotional information and rational. Anyway, I was very confused. So then I realized that some of my talk was inappropriate. And anyway, I should start my talk now. Biology and the origin of information. So what I have here is the CMB, and then we have like the early Earth, and then we have the code, the DNA code to turn triplets of base pairs into the amino acids, and then we have the program. So information's dependence on biology is the topic I want to talk about. And abiogenesis is a fancy word for the origin of life from non-life. And I guess infogenesis is the origin of information from non-information. And I'll try to make an analogy between these two processes. And I think to understand life, we need to look at its origin and history. And I think I want to change that sentence. I don't know who wrote this talk, but it should be its origins, because usually when you think of the word origin, you think of something simple in an event rather than a process. And most of the thing I want to say is that this is a process we're talking about. So, and life is the same thing, and information possibly the same thing. Now, as physicists, we're used to thinking of definitions of things that are valid for all time and presumably everywhere else in the galaxy and the universe. But in biology, it's a little bit different. And I want to talk about that. So is all information coded information? Well, over here, this is coded information. You can see the letters you're used to, 26 letters of the English alphabet. And then here's coded information. This is a code that evolved before there were vertebrates and before there were multicellular organisms. This is very early, but there are some variations to that code. For example, the mitochondria inside each of your cells uses a slightly different code than this one. And then here we have the early Earth, and it was bombarded, and there's the moon being hit by something. And there's nobody around here. There's no life. And all this information is really some human made a picture of something, or some artist. So that's the information we have currently about a time when there was nothing to register the information. And I'm not sure whether register and processing are the same. And then here's the CMB that we made in 1992. Okay, so is this uncoded information? Because there's no one around and there's no code, because codes have to evolve. Code is not something that, you can talk about like before the Big Bang or at the Big Bang. Codes have to evolve, so all coded information depends on life, I would maintain. So what is the role between information in our universe, between biology, information, and entropy? Now, I'm a physicist, astrophysicist, so physics, I think, can be summarized as a search for fundamental ahistorical quantities like mass and energy. I say ahistorical because we want this definition to be valid now, 1 billion years ago, 4 billion years ago, 13 billion years ago. We want to have a definition of something we can talk about and extrapolate as far back in time, as far future in time, and in other places in the universe. That's the kind of definition we call universal. That's what we want as a physicist. That's why a lot of us have become physicists, because this universality is something great. If you're qualified to practice as a physicist on Earth, you're qualified anywhere, even on Andromeda. But biology is almost the opposite. Evolutionary biology is a historical science. The study of life is the study of the time dependence of life's features. So for example, consider you have a head right now, or you have a head. Now, how old is your head? Now, we have a definition today of a head. Everybody can agree on that. But let's go back about 400 million years, and then the heads start to turn into the front end. And then you go back another 400 million years, and then you have a couple of overdensities of neurons in the front part of whatever animal we were talking about. And then go back earlier than that, and then, your head, in other words, you're talking about proto-heads, proto-proto-heads, proto-proto, and this is characteristic of everything that you can currently define in biology, as when you go back in time, it gets deconstructed, it disappears. Why is that? Because it had to come from non-life to its current state. So a head, although we think we can define it, is not a definition that you can extrapolate in your time machine. Question over there. Speak loudly. Yes. Okay, so the question is, what's the difference between a caustic and a head? Okay. And, well, I guess one reason, I'll be talking about far from equilibrium dissipative systems, so maybe let's hold off on that because I really want to address that issue more completely in about 10 slides from now. So I think there is a big difference. Basically, the difference, I think, is information content inside of the caustic or inside of the DNA that produced the head. Phenotype, okay. So the study of life is time dependence of life features. Now, I guess my main idea here is that information, the word information, is more like a head, in the sense that we can define it now, fine, just like we can define heads. But if we go back in time, what do we mean by, as physicists, we're going to put this information in the future, in the past, in other galaxies. But I don't think that's necessarily legitimate, of course, depending on what you mean by information, what you mean by processing. So Seth, when you have virtual fluctuations, is that virtual processing of information?
Because the virtual fluctuations in the vacuum are just an energy eigenstate of the quantum system. It doesn't change.
Okay, Seth says no.
So it's got 0 bits of information.
0 bits of information. Okay, we'll talk about that later. Anyway, so I would maintain that this word information in many ways is like life, and life also suffers from the same problem. We think there's non-life and then life, but we as physicists and biologists know that life had to evolve from non-life, but it didn't go like that. First this happened and this happened and this happened, just like the story of a head. I talked about the origin of heads, and people said, oh yes, what about cabbage heads? And what about corals? Corals have heads because they have brain coral. But anyway, when you get too much free association, the ideas start to fall apart. But the main idea here is there might be a difference between a platonic thing like pi, which you can define, which doesn't evolve, and things that do evolve. And then I just substituted it for information in here. Is information an unchanging platonic form like the number pi, or does it have a stable, unchanging definition, the kind of definition that we physicists would like to have, because then we can project it everywhere, back in time and different places? And the answer for Friedrich Nietzsche, I ran across this in a book called The Genealogy of Morality, is no. Only that which has no history can be defined. Only that which has not evolved can be defined. What he meant by that was you can define it, but that definition will not hold in different times or different places necessarily. So he's not, and so the same thing I think can be said of life. Life is something that has evolved, but we think we know what life is now. You say to anybody in the street, this is live, this is not live, and everybody agrees. But if you go back to close to the origins of life, and ask that of a RNA molecule or some molecules that are kind of the proto-life, proto-biology, and say, is that alive? Well, I say necessarily you will run into that type of thing. And so that means that don't have too much confidence in whatever you think information is, I guess is another way to say that. So here's Jack Szostak. He's somebody who in the astrobiology community, he's trying to understand the origin of life with chemistry. And he was so tired of people trying to define life that he wrote a paper against trying to define life in a way that is specific, that they would then go to extrapolate not only to the origin of life on Earth, but trying to find life elsewhere. We are trying right now, there's so many planets, we're trying to find an Earth-like one in which maybe there's life. But then you say, well, what is life? If we're going to go search for something, we should know what it is. But then they say, well, wait a minute, the definition of life is something that, like the definition of a head, changes with time necessarily. And I think that's his point here. So, and then I would just substitute the word information for life, and you have the same thing, because similarly, information is something that has evolved, I would maintain, and life, the same thing. Go ahead.
Physical definition of information, Shannon definition of information, minus some has it changed?
It didn't even exist at the beginning. The beginning was Shannon, 1948. Okay, well, so you think there's two definitions of information? Because Eric can think of 20.
I just wanted to make a mark.
Right, okay. No, and so there is a disagreement about whether information is dependent on biology or not, right?
Yeah, the physical definition of information is perfectly fine.
Okay, well, that's wrong. He says the physical definition of information is... Okay. Well, but anyway, I guess we would agree that there are different definitions of information, and they have changed over time, and depends on which one you mean, I guess. Well, how about coded? There's another word. You have to talk about information that has no semantics. Right. Right.
May I have my take?
Yes. Yeah. I'm supposed to repeat everything that's being said. These people are. Go ahead.
But there was a reference to Shannon.
Yes.
The title of the paper is Information and Communication Technology.
Yes.
Not only information, communication.
Yes. Well,
and actually,
I would say not information, but the communication of information, right?
Let me make my point.
Go.
Because you were so kind to tell me that you read my book on the way in the plane here. You might have noticed that in my book, the word processing is hardly mentioned.
Yes, I did.
Actually, the most useful definition I found in my book is information is best described as the copying of information.
Right, or the translation,
processing.
I guess.
So that eliminates processing, because processing is actually nothing else than copying information. So that closes all this discussion, makes it very simple.
Okay. Well, this is Shannon. There he is. He looks kind of deviant. Anyway, this is life, the father of information theory. The meaning of the message is generally irrelevant. Now, when he said that to a bunch of biologists, they kind of object, because for a biologist, all information is meaningful. And if it's not meaningful, who cares about it? It's not there. And that's one of the problems in trying to define information for biologists. Because and what is significant is the difficulty in transmitting the message from one point to another. Of course, somebody who works for IBM and Bell telephones would say that, because it's the transmission. He doesn't care what the people talk about as long as they get there without making mistakes. But that's not what biology is about. Anyway, I recommend this book here by James Glick. Here's James. And he wrote information. He's kind of summarizing his theory and other theories of information. He said, information is closely associated with uncertainty. Some messages may be likely than others, and information implies surprise. Now, the more surprising a message, the more information it contains. Now I'm thinking, well, what determines the degree of surprise? The reason I'm asking that is because a lot of people say, I see a lot of science journalism, we say, this is an incredible result. It's much larger than we thought. And I'm saying, who is the person who has this bad theory that doesn't correlate with this result, who thinks that it's a surprise? In other words, the worse your theory, the more you are surprised by experimental results. So if somebody is not surprised, then I say, oh, that guy's got a good theory, or any scientist. So anyway, what determines the degree of surprise? experience, context, neural architecture, DNA, all the features of life. Can the universe without life be surprised? And what can surprise mean in the universe before life existed? And probably you could say, I guess, well, whenever the probability of an event is low, but I would say that depends on the observer who's talking about that. So if information is the reduction of uncertainty, whose uncertainty are we talking about? If you need a who to talk about uncertainty, then you need life to have information. But as I argued earlier, life and information, I have as historical concepts are things that have evolved. And therefore, when you define it, you're defining it at one particular time. And earlier, it didn't exist. The definition didn't exist, and therefore, information didn't. At least I would wave my hands and argue that. There's something in philosophy called perspectivism. This is interesting. I think this is what I must be relying on. It says you can't have a view except from a viewpoint. There is no viewpoint independent information. At least that's the idea. And I think this is Nietzsche who agreed with this. And I think I agree with it. But if that's the case, then a viewpoint implies there's some information that you are processing inside a brain or inside a ribosome. And if you don't have a viewpoint, you don't have a view. And I think there's something to be said for that. I'm not quite sure I'd defend it with my life, but maybe with $1. Okay, and here's the viewpoint that we have. This is the Voyager pulsar record, and here are the pulsars in their different directions and their pulses. And this was put on the Voyager record so that when aliens find this record, they will know where our viewpoint is. And that's what this little green dot is supposed to represent in our galaxy. So they're coming for us when they can decipher this. So early in the history of our universe, there were 1 billion particles of antimatter and 1,000,001 particles of matter. They annihilated, produced 1 billion photons, actually 2 billion photons, and 1 particle of matter. We are the 1 particle of matter. And in 1992, we took a picture of those photons. It's the cosmic microwave background. This is what I did for my PhD. There it is. And I know, Edwin, you might be interested in this because, as an astrophysicist, we know that red is cool and blue is hot, at least for stars. And George Smoot, who decided the color scheme for this image, he said, well, that doesn't make any sense. Most people think, and most hotel faucets on hot water, they have red is the hot and blue is the cold, which is just the opposite. And it's even more misleading because this is a millimeter wavelengths, not anything to do with the optical wavelengths. So in many ways, this is wrong. Remember, you just take this picture and wrap it around your head and everywhere you look. And the right there in the middle is the galaxy. And notice that every time there's a new experiment, a full sky experiment, from Kobe to WMAP to Planck, the universe changes color because I guess the principal investigators don't like to have the same color scheme as what we just did earlier. And that's a weird thing that's a little bit misleading. Anyway, imagine a universe with no asymmetry, no matter asymmetry, a universe with the same amount of matter and antimatter. The matter and antimatter annihilate, leaving just photons. There would be no galaxies, no stars, no planets, no atoms, just thermalized black body photons. There would be no one to take a picture of it in 1992. Such a universe is at maximum entropy, a universe stillborn in a heat death, a universe with no life, no observers, no cameras, and I would maintain no information, despite the fact that we can write down a formula, according to Shannon, for information transmission. And now here's another alternative. Now let's go back to a universe with matter in it, but let's say the expansion rate was so high that galaxies, stars, and planets could not form, thus there would be no life. Would there be information in this universe? And I guess you can talk about this, but I'm not quite sure we know the answer because it depends on what definition of information you're using, but also whether you are meta thinking, like I'm trying to meta think about, we invented this Shannon entry in 1948. In 1942, it didn't exist, this information, although we pretend now that it did. And I would say that you have to take into consideration the history of what you're talking about, of your model, if you want to talk about the history of the information. That's, I guess, my ploy, that information, like life, is a historical thing rather than some absolute definition that we physicists love. So I did an informal survey. Can you have information without biology? And a quarter of people said, no, you can't. These are mostly biologists. A quarter said, yes, these are mostly physicists. I think a quarter of, I don't know, and a quarter would say the question doesn't make sense. So I would say that this disagreement is good evidence that unlike mass or energy, we do not have an agreement about what information is. And more than that, it's not only that we don't have an agreement. I would like it if we could agree on evolution as, there's a question over there, so please, yes, speak up, please. Let me stop. So the question is it possible that I'm confounding the amount of information in a system to the concept of information itself? Well, I would suggest that if you get into a time machine and go back, I don't know, let's say 100,000 years and ask something about, 1 + 1, and well, if you go to kindergarten, for example, and talk about the concept of addition, I bet you get a bunch of different answers. And we have standardized that. That has been congealed into this mathematical plus sign that we all can agree on. But there's a long time before we could agree on it. It's much like the concept of zero, right? That took a long time. The Indians invented zero, but it took a long time. Now, why did it take a long? In other words, these concepts that we now hold as fixed, as like physicists, are not like that. They have developed historically. They have a history. It's complicated. They have evolved. And I think we should admit that. I don't know if that answers your question. Yes. Well, I think I would argue that yes, it does. If your concept is changing, then what you're talking about is changing. Yeah, another question. Yes, Bernard.
Yeah. There's a question here which is not being addressed, and it's about meaningfulness.
Okay, there's a question here that's being addressed, and it's about meaningfulness.
The point is, somebody would speak to me and convey information in Chinese.
If somebody were to speak to him and convey information about Chinese, he's talking about Searle's Chinese box experiment here. It would not be meaningful if he heard, because you don't speak Chinese.
And there was a Norwegian philosopher called Follersdal who said meaning is the joint, the combination.
There's Norwegian philosopher called Follersdal.
His argument was that meaning is the evidence.
His argument was that meaning is the evidence.
The evidence of all those provided by all those who communicate.
The meaning is the evidence. The evidence is the meaning.
Meaning?
The meaning is the evidence that all.
Evidence.
The evidence of communication.
Provided by all those who communicate.
Is the evidence of the
It is
meaning.
basically essential to making what you do meaningful. And I would probably assert that I would be among the question doesn't make sense. Because we're not talking about evidence in that everything is meaningful. Information has to be meaningful to be useful.
Well, that's for a biologist, yes, but for not for Shannon. That's exactly what he said was not the case. He said, I don't care about the meaning. I just need to care about the transmission. That's,
I think we are mixing up information and knowledge.
Information and knowledge and wisdom and stupidity. But anyway, let's continue here. There are more questions. Okay, more questions. Yes, who? Over here. Yeah, given that's easier for me. It's harder for me to repeat the question because they're so long.
You're talking like biology is separate from physics.
I am. That's exactly right.
Chemistry, biology is sort of effective, right, derivative of theory from physics. So if you think about information in physics and information in biology or biology itself, right, even the concept of information is an effective theory of the concept of information in physics. And right, and usually you can.
Right. So the question.
In that sense, right? Yes, there can be multiple definitions of information, but they're not fundamental.
Okay. So this is the story is biology depends on biochemistry. Biochemistry depends on quantum mechanics, and quantum mechanics depends on physics. Therefore, physical concepts trump the other concepts because they're more fundamental. The answer to that is that all physicists are biologically evolved creatures. So all physics depends on biology. So I'm just going to reverse it on you and say, you would not be talking anything to do with physics unless you had evolved as a biological organism. That's the first thing. That's for biology. So anyway, that's, yeah, I would say physics didn't exist before physicists, and life forms didn't exist before life evolved. No, it's not. It's a life-centric point of view, but anyway,
So
it's an evolution-centric point of view.
We had a question in the back
Okay.
first.
Loudly, please.
really exist because or the concept changed over time.
That's right. It's very important.
And our understanding, but our understanding of mass and energy also evolved over time.
Yes.
Didn't that exist? Didn't that exist before us neither then?
Well, no. About what was it? 200 years ago, we had kinetic energy, we had potential energy, we had heat, and then somebody said, "Oh, you know what? This is all the same thing. We're going to call it energy." And Einstein said, "Hey, even we have gravitational waves are energy." So the concept of energy has evolved, and it may evolve even further depending on some of the nicely weird ideas that we're hearing here. But we like to think that we have the most universal version of entropy possible, that we can have confidence when we look at a spectrum from a star or a quasar that's 10 billion years ago. But I'm looking for something analogous to that to look for life elsewhere. And I think if we focus on, okay, what is life? And we don't recognize that life is something that has changed and evolved. And if we try to define it now, it's absolutely crazy. Even in the history of life on Earth, doesn't make any sense, because you have to go back earlier and they're like heads, they get deconstructed. Every historical process is like that. That was Nietzsche's point, that you can't define something that has evolved. Or rather, to be more specific, you can define it now and it makes sense now, but you have little chance of it being valid or useful as you go back to different times. Okay, we have a philosopher here who says that's correct. How much time do I have here?
11 minutes. Do you want to continue now? Or
Yeah, I'll tell you what, let me go through a little bit more and then we'll have another question. Okay. Anyway, now I have recently made a course, an online video course called Are We Alone? Right here, arewealone.us. You can just Google it and you can log in, and it's a video course about the question, are we alone, and the different aspects of it. Most of it has to do with biology. So I recommend that. But as part of that course, I was trying to figure out what life is. Now viruses are some type of thing that are kind of lifelike, or maybe life, or maybe not life, but they are the most abundant organisms on the planet. They outnumber the bacteria that we heard about in the previous talk by a factor of 10, maybe even more. So viruses are organisms, and whether they're life forms or not depends on how you define life. So I said, you know what, I'm going to go ask a bunch of people, are viruses alive? And 1/4 of them said, no, they're not, because they're parasitic. They need other life forms to exist. And then about 1/4 said, yes, they are alive. 1/4 said, I don't know. Question makes sense, but I don't know the answer. And then 1/4 said, the question doesn't make any sense. And I'm with this last 1/4 because I don't think the question makes sense. Why? Because we don't know what life is. We pretend that we know what life is based on our current definition. But you take that back into the past, that definition becomes crap. Why? Because we know we have to use something to go from non-life to life. There's a transition there, and we have to understand the historical transition rather than impose a current definition of life that we have now. So that's what's going on here. And that's why I suggest 1/4. But this disagreement, I think, is good evidence that unlike mass or energy, although there are caveats here if people wanted to redefine that, we don't have an agreement about what life is. There's no well-defined boundary between life and non-life. So it's very, very easy to think, oh, there's life and there's non-life, life and non. I mean, every one of us has heard that dichotomy pounded into our heads. And the more I look at this, the more I disagree with that. And that's what I am getting so emotional about this question. Okay, so here's some definitions of life. As an astrobiologist, we're really interested in this because we're looking for life on Mars. We're looking for life in the clouds of Venus or maybe on Enceladus. We're looking for signs of life from other civilizations, with radio telescopes, for example. Or we're looking for life with biosignatures as planets transit in front of their host stars, and then we can see molecules that are out of chemical equilibrium. That is, we got some redox potential that maybe is being produced by life. It's kind of like the oxygen that you're breathing right now is everywhere, produced by life, and we use it to get free energy. Anyway, so here's one. This is NASA's favorite definition: self-sustaining chemical system capable of Darwinian evolution. Jerry Joyce, 1994, he published this. And I said, well, what? So there are 2 words in here that I want to object to: self-sustaining. I don't know what that means. No life is self-sustaining. Life is obligatorily dependent on other life forms. Just like you take a male and a female, put them in a spaceship, put them in outer space. They will not reproduce. They will die. Why? Because they'll run out of oxygen, they'll run out of food. They are obligatorily dependent on other life forms that are producing the food, producing the oxygen, so you can do the respiration. Also, yeah, so you are using oxygen from photosynthesis, but also viruses are using your ribosomes to make proteins. How is that any more parasitic than us parasitizing the oxygen in the atmosphere? I don't know. Now, what he said, self-sustaining chemical system capable of Darwinian evolution. So we can ask the question, did Darwinian evolution evolve? Or is that something, oh, you turned it on like that? I would suggest you can't turn this on. This is something that has to have evolved. So, for example, horizontal gene transfer produces acquired traits that are passed on. That's when you have two organisms. Now, instead of having sex, they said, hey, I have a gene here. You can't deal with the salt tolerance. Here, I'll give you a gene. Oh, that's great. Now I can live. That's horizontal gene transfer. They're not having children to pass on with mutation, but rather a specific exchange, just like we exchange words. That's what we're doing now. That's horizontal gene transfer, and it's passed on. So much of early evolution is horizontal gene transfer, and thus it is Lamarckian, not Darwinian. And so the definition, I think, just falls apart for that reason as well. And what about the evolution of the unit of selection, this chemical system that he's talking about? There are other objections too, but I won't mention it. Now, Eric Smith in the audience, who's the next speaker, had this to say. He said, a chemical system in which the flow and storage of energy are related to the flow and storage of information. So energy, okay, we're physicists, we have probably a good idea of what energy is, maybe. But information, I don't think so. Coded information only, is what we're talking about here? When he said, or any information that can be passed on. In metabolism first models of abiogenesis, there is no coded information. Sometimes there's a model by Segre and Lanson called composomes, where you have an organism. There's no DNA, no coded information, but you have structural information. That structure enables you to pull things in through your protein, through your cell layers, and then put things out, and then you get bigger and bigger, and then you just divide in half. So the structure is being passed on without that information being coded. I call that architectural information. One other thing, free energy and entropy. So here's Erwin Schrödinger, and here's Ilya Prigogine, and they talked about life. What is life? Read that. And he talked about far from equilibrium dissipative systems. So from a thermodynamic point of view, living systems are an instance of a more general phenomenon of far from equilibrium dissipative systems. So what are those? Here's some pictures of some far from equilibrium dissipative systems. We have, I don't know, galaxies, some stars, convection cells on the sun, a whirlpool, a hurricane, Jupiter, tornado, lightning in a volcano, life form here, wind pattern here, some chemical reactions, and then this is the JWST image of the star. Anyway, these are far from, they're organized structures. Obviously, they have a lot of structure to them. They are not diffusion of any kind. 5 minutes, okay, thanks. And so you can ask questions like, oh, I had a colleague who said, I think stars are alive. And here's the reasoning. He said, well, there's a metabolism, it's called nuclear fusion that occurs in the center. And there's reproduction because the explosion of one generation produces the next generation. Then there's inherited information, elemental composition that goes into the molecular cloud, which then gets condensed into the next generation of stars. That elemental composition also changes the initial mass function of the next generation of stars, so you can have evolution. I think Eric Smith would call this free association, but I think there's something to this. Now, here's the surface of the sun. Each of these are convection cells about the size of the moon. And this is an organized structure, a far from equilibrium dissipative structure that has been produced by the heat gradient between the lower levels of the sun and the surface. And that is transferring energy, creating more entropy than would be the case if it were just diffusion. And so everywhere in the universe, when there are these gradients, if they're strong enough, they produce these far from equilibrium dissipative structures what do? They increase the entropy of the universe faster, of the structure, faster than would be the case if they didn't exist. So we wrote a paper about this, and we can eat food. We eat food, that's one, when we think we eat food, but I think a better way is food has produced us to eat it, much like aerobes were produced by biology to take care of the oxygen problem that was building up because they had all the plants doing oxygenic photosynthesis. So what about fakes, facts, and fakes? I took this term from your book, Facts and Fakes in Biological Information. There's some interesting features about biology that are different from what we think we're doing as scientists. So here's what biology selects for. It selects for things that are useful. Here's what we think we're doing as science. We think we're looking for the truth. Now, these two sets overlap. And when you do, you get useful untruths. Remember, this is all useful. And here are the useful truths. And here are the useless truths. But because we are biological organisms, we have been selected to live here. So in our brains, we have both useful untruths and useful truths. Inevitably. Now, I drew these boundaries a little bit blurry because what is useful can depend on the environment. Sometimes, for example, if you were an atheist 200 years ago, you'd be killed, and now we tolerate atheists. So the belief in atheism is something, or Christianity, they're burning Christians because they did believe in this kind of God. Anyway, this is a blurry thing depending on the environment. And here are the useless truths, a lot of, anyway, there's useful truths as well.
Charley, if you want some more time for questions.
Yes, okay.
So as a professor of mechanical engineering, I say mechanical engineering is full of useful untruths.
As a professor of mechanical engineering, Seth Lloyd says that mechanical engineering is full of useful untruths.
Like classical mechanics.
Like classical mechanics is the example he gives. I wouldn't give that example, but there are many, many others. Because any other questions? We have can you run over here? Here comes 3 seconds. 1, 2, 3.
The categories truth and falsity are artificial.
Say it again.
The categories truth and falsity are artificial.
Uh-huh.
Falsity can be invisible truth, and truth can be invisible falsity. So we, the philosophers, are trying to go beyond categories because there is a continuous movement between the two categories, between truth and falsity. The truth becomes false, the false becomes truth.
Are you using categories to go beyond categories?
So we must go beyond the categories. We must go to the neutral.
Go to the neutral. Okay, so you want to get rid of the viewpoint.
The constant and the neutral.
Okay, all right. I'm not sure what to say to that, but thank you for that. I'll show one more slide. So I want to say that useful untruths and useful truths both get coded as biological information. The brain you're using right now has been selected for useful whatever. That includes untruths and truths. Whatever is useful. That's why you believe so many crazy things. That's why you look on the internet, you see all that crazy stuff that people believe, because they've been selected to believe for usefulness. And to pretend that that's not what your brain has evolved to do is crazy. It's unscientific. You have to, as a biologist who believes in evolution, you're using your brain. You know that this is what has done, this is what has created you, not this that we get told, hey, we're looking for truth, we're looking for truth. We're not. We're looking for useful whatever. Question over here?
Thanks for the energetic presentation talk. I wonder what do you think? How do you think the Stephen Wolfram approach to the ruliad and ruling in this in a sense that it's kind of underlying universal processes of organization and information, although there are jumps.
So when I went to see Green Day, I was thinking of all these wonderful people enjoying music, and I said, "What are we doing here? We must be bounded observers of the ruliad." And when I asked Stephen, "Can you show some evidence? I'm a scientist. I want some predictions, a test we can do to see if what you're saying, if your map of the world, if your model of the world is accurate." And he mentioned twice the dimensionalization, changing of dimensionalization. He threw that out at us physicists as if we could easily say, "Okay, here's the test for the different numbers of dimensions." And I wish he had been more specific about that. That's what I think he should hire a postdoc to turn that model into predictions that are slightly different. There probably are slightly different than standard GR or standard quantum mechanics or other already accepted and tested physics.
Okay, thank you, Charley, so much. That was really great. But now we have to move on.
Okay.
Thanks also to the audience for being so enthusiastic and having so much input. So now,
Right.
yes, you can continue the discussions.